Welcome to ARC. It says an introduction to Semi-Truck Aerodynamics, but I should probably start just by talking about ARC a little bit. We started off working with the race teams for IndyCar. That's why we're based in Indianapolis. That's why we built the wind tunnel and the test facilities we have here. And we've grown from there, working with other manufacturers on production cars, in trucking, and we've also grown in the facilities we have. Most recently, which we'll also be talking about here, is our Cfd Department. So we now provide a whole range of facilities for testing for automotive, and that really helps us in bringing everything together. So we can take a truck, we can scan it, we can create the model of it, we can do the drawings. Next door, that's the engineering office where we put the drawings together. We can make the models, we can test them in the wind tunnel, we can test them in CFD, we can analyze the results, we can make improvements. There's not many places where you can actually bring all of that together in one roof. So that's just a little bit of background to what we do here. I'll start off just making sure everyone's familiar with aerodynamics, because that's a lot of what we look at, particularly what I'm interested in. It's what helps planes fly. Aerodynamics is, technically, it's the study of movement of air. We're usually talking about it to determine aerodynamic forces, lift, drag, side forces. All of these are of different levels of interest to different people. I assume to most of you, the trucks are more interesting. And they can be very interesting, aerodynamically at least. This is just some other examples of where you might see the effects of aerodynamics. Obviously, one of the biggest challenges with developing vehicles to be aerodynamic is that we can't see what the air is doing. But on a rainy day, you can see the spray being thrown up, and you can start to see some of the structures in those examples there. There's a lot of factors that affect the forces that a vehicle experiences, but we can simplify that quite a lot. For highway speeds, for a truck, 90% of the drag is just due to the differences in pressure on the front and the back, not just of the truck, but of every component, the front and back of the wheel, the front and back of the trailer gap there. So ideally, the pressure would be the same, there wouldn't be any drag, but that's not something we can achieve. So it's all about trying to reduce that difference in pressure as much as possible. One of the key things that affects the flow in, well, all vehicle aerodynamics is where the flow separates. You probably have some idea of what separation is. It's what we were looking at there around the wheels, where the flow just becomes very turbulent. It's hard to predict where it's going. It's messy. It wastes a lot of energy. Essentially, once the flow is separated, we can't recover the pressure. I don't want to get too technical, but if the flow didn't separate, we could get back to the same pressure at the back of the truck that we do at the front, and we wouldn't have any drag. But because flow separates, and that's just due to viscosity, it's unavoidable in this universe. We're always going to lose some pressure as we go past an object. But the reason we look at this is if we can reduce the separation, then we can reduce the drag. So it is really a very good way of judging how aerodynamic a certain shape is. This desk's in the way, Christy. So just coming back to the forces, a lot of this is just to give you a little more structure to understand some of the results which will be presented later. So we can look at the different forces, and we normally express them as a coefficient so that we can compare between different size vehicles and at different speeds. So the coefficient gives you an idea of how efficient the shape is. It's coincidental, the words there. It doesn't necessarily mean that a lower drag coefficient has less drag. It just means that if everything else was equal, if it was the same size and traveling at the same speed, it would have less drag. So for example, you can reduce the drag on a vehicle by making it smaller. That seems obvious, but sometimes we have to remind people that if you change the size of the vehicle, then your numbers will change. That doesn't mean that you've necessarily improved the efficiency if you're looking at drag coefficients. And this is just some more technical detail. Some of the theory that allows us to do the work we do. The Reynolds number is one you may have heard of, most likely to have heard of. Essentially, this is what justifies scale model testing. This is the theory that says that if we make the model smaller but run the air faster, then we should get the same result. Aerodynamically, it should look the same. It also means that if we test something at 30 miles an hour and it shows that it's an improvement, it should still be an improvement at 60 miles an hour. Some of this may seem kind of intuitive, some of it is less intuitive, but it's kind of the basis of a lot of the work we do, is to say, okay, we can't always test exactly in the conditions we'd like, but if we understand the differences between what we want to test and what we're able to test, then we can still use the results, which is really important. Why is it important? That worked nicely. These numbers, I'm sure you can, you probably all have more accurate numbers, but essentially at highway speeds, the key thing is that aerodynamic drag is about 50% of the losses of the truck. The rest of it is in the powertrain and rolling resistance, which you address through other ways. But aerodynamically, as you get faster and as you get up to highway speeds, drag is a significant proportion of the losses. And so if you get a 10% improvement in the drag on your vehicle, then that's a 5% saving your gas bills. So particularly with a lot of the add-on parts for trucks, you can spend quite a small amount of money and make it back very quickly, because it's an area that hasn't really been exploited. It's a lot more common now, but it's still really quite early in terms of what's being done to improve the aerodynamics for trucks. Obviously, this isn't the worst time ever in terms of gas prices, but they probably will be going up again. And also, it's not just the price, but the emissions standards that need to be met as well. So reducing your fuel usage, I know you all know, is well worth doing. And how we measure that is this quantity called wind average drag. We do a lot of testing and verification for the EPA with their SmartWay program. We've actually done a lot of work with them in developing a lot of the standards in our wind tunnel here. And this is somewhat arbitrary. It's just necessary to have a fixed number to be able to compare between different trucks, different models, different improvements. And all it is that we test essentially at different crosswind speeds to try and represent what a realistic driving cycle would be in the US. And then there's a calculation to create a wind average drag. So it's just a weighted average of the drag with different crosswinds applied, which is what is used for all the standards to be able to show whether a particular add-on part is an improvement or not. That's how they determine your fuel efficiency. And more specifically, the ways we can then measure wind average drag or any of these aerodynamic forces, track testing, which will be talked about later, wind tunnels, and computational fluid dynamics. All of these have different advantages for studying aerodynamics. Track testing allows you to have the real physical truck and the parts. That's one advantage. Another advantage is that you're using the real physical world, which helps. However, you don't have a lot of control over what the environment is. And particularly when you're trying to look at a wind averaged drag where you need to test that specific crosswind conditions to satisfy the standards, that can be quite involved to achieve consistent results to be able to prove an improvement. Wind tunnels allow us to control the environment. We can test at a certain wind speed and angle, and we can repeat that, and we can come back a year from now and we can control everything again and get the same results. And so you can compare a lot better with that. You're still somewhat limited in what you can actually see happening. And you still have to build a physical model. It doesn't have to be the full model. We can use scale models, but you still need some kind of build time to test parts. CFD, we're no longer in the physical world. We're in something very similar. So that's the drawback of CFD. The advantage is that we can see everything that is happening, and we can make changes, we can test different parts without actually having to build anything. It's all virtual. So right now I'll just talk a little bit more about CFD, and then we'll be able to talk more about the wind tunnels in my second part of my presentation when we'll go down and see the testing happening down there. It will look quite a lot like this, but it'll be noisier. And then, as I say, track testing, there'll be a presentation on later. So I like talking about CFD because I finally get some nice pictures to put up. CFD's been around for quite a long time because all it really is solving equations that, I mean, the complete form of the equations we had here in 1822. So the challenge with CFD has always been having the computational power to actually do a large problem quickly. We've known how to do it for quite a long time, but it was only, I'd say, in the 1950s we were actually able to start using this on vehicles. They were using it earlier in aircraft because the flow over a wing is actually relatively simple to compute compared to and this is again due to the separation. The separation is the challenging part to simulate, to predict. So it's relatively recently that we've been able to use CFD in the automotive sector for real scale problems. And even more recently than that we've been able to do what we consider the necessary level of detail, which is to actually have time varying transient simulations. A lot of the earlier codes for aircraft were an averaged flow over time, which is easier to solve, but not really accurate when the flow's changing a lot over time. And that hopefully seems obvious. And again, that's just a question of having the computational power to be able to do that within the design cycle. So I also get to have some fun animations of this is just some work we did recently for IndyCar. Just showing some of the flow structures that we can see. As I said before, in CFD, we can see everything, we control everything. It's like having 100 million pressure taps all throughout the flow and all over the body. Sometimes that is more data than you really need, but in terms of development, after a while of going into the wind tunnel, or going to the track and testing parts over and over, and you see the numbers change, but you don't really know why. When you can start to actually see what's happening with the flow, you can put those things together. I went too fast. There we go. It's a truck. I know you like trucks. We can do the same thing with trucks. That's all we're saying there. And here is just, this is a cross-section through the air moving back along the length of the truck. And this is just showing the total pressure, I would say. And anywhere where it's not red, this is where we have separation. This is where the flow is losing energy. This is areas that are causing drag. And you can see just how much information we can get to study what the flow is doing on a model like this in CFD. So the benefits, hopefully I've made reasonably clear. You can control what you want to test. You can set whatever wind conditions you want. You can even have the truck running in something other than air. You can simulate it as water if you like. It's a very trivial change to the equations. Not that you'd want to, but if you did, if you were comparing to testing in a water tank, for example, water tanks have been used for truck testing because, again, going back to the aerodynamic similarity parameters I talked about earlier, so long as you apply that theory correctly, you can see the same flow structures pulling a tank very slowly through water as you would by moving it quickly through air. The physics is the same. So a lot of what we can do in CFD isn't necessarily about finding improvements in the real world. It's about trying to simulate what's happening in actual other test facilities, in wind tunnels. We can simulate all that detail as well, and that can help us understand why different wind tunnels give us different results, or why a wind tunnel gives us a different result to on the road, because we can actually start seeing what's happening to the flow that's different to what we expect. And then it's very easy to make those changes. There's no physical cost to building complicated parts. You don't have to, I mean, you don't even have to make the model make sense. You can have different parts of geometry that just hang in space in the CFD model. It doesn't need to be attached to anything if you just want to quickly see what effect something like that would have on the aerodynamics. So CFD, obviously, it takes longer to do a single test than wind tunnels, but it doesn't take so long to prepare for it, and you get a lot more information out at the end. So they're very complementary, as we'll hopefully see when we get to looking at the wind tunnels later. And this is a final example, I think, of just a better illustration of the breadth of what can be achieved. There's no reason we can't do this with trucks as well in different positions. And again, you can look at all the flow interactions. You can see how a truck in traffic is behaving differently, why the fuel economy changes compared to the tests that we're just doing. This is very hard to do in a wind tunnel. It's, I guess, easier to do on track, but to do it repeatedly, to actually have the same distance between the vehicles every time when you want to go and put on a new part and then see whether it's an improvement or not, you have to run the exact same test. That would be pretty challenging as well, until the trucks can drive themselves, in which case that's more manageable. So there's really a lot of potential, so long as you're willing to have a bit of imagination about what the CFD can do, and how to relate that to what you'd see in the physical testing in wind tunnels and on track, and bring it all together. As I say, you won't necessarily get the same answer in CFD, because it's not representing the same physical conditions exactly, but we often get very close. And well, actually, I think that slide comes later. We have some results here for the wind averaged drag on a truck. The wind average drag is within 1 count, which is a fraction of a percent. So it can be very accurate. We get some very good results on trucks.
Can you talk a little bit about what roll down testing is?
You mean coast down?
Coast down. We will be talking about that later. It's basically a more controlled version of track testing, where you're eliminating the powertrain from the losses. So you know that then all your you start the truck up, you then just see how long it takes to slow down, and that tells you how much drag there is from the air and from the tires. So it gives you another piece of the puzzle. The one thing I kind of want to stress from this is that there's really no best way to do the testing. There's flaws with all of them, but if you look at the whole picture, then you can start to have a very good idea of what's going to work and what isn't. I believe that will bring us to the last slide for now, if that's okay, unless we want to move on to wind tunnels later. This is just a very quick run through of other applications outside of aerodynamics, which we can easily extend the CFD to. As I say, we can change the environmental conditions. We can also study thermal issues under thermal management. It's relatively trivial to just add an additional equation and simulate heat in the engine bay and component cooling, the heat exchangers. We can also simulate the flow inside the cabin with HVAC and look at soiling. A little bit more challenging that, but it is possible and certainly easier to clean up than in the tunnel. It decided to move on for me. Was that you, Christy?
Was it?
Maybe. Anyway, that just very quickly running through there. There we go. Yeah, we can simulate. We could simulate the flow through the engine. We don't typically do that here, but we can simulate flow going into the engine and exhaust flow as well, which in some applications is significant. CFD in general, I mean, we have the tools to simulate the combustion within the engine as well. That's just not something we've done a whole lot of work on improving.
Have you been asked to do any testing as far as with skirting, what we're doing to the trailer, as far as wheel end temperatures and what we're taking away? We're taking away cooling from the trailer, brakes, seals,
Yeah.
and so forth. Have you done any testing on that to see to what extent we are taking away that cooling?
Not that I'm aware of, certainly not in the CFD. I don't think that's something that's been looked at in the wind tunnel either. I mean, it's something we've done with production cars, with race teams, looking at brake cooling impact. So it's something we certainly could easily do with the skirts, but I don't think that's an issue that anyone's talked to us about measuring. So I mean, that is exactly the sort of thing we could do in CFD easily, because once we have the model, we're looking just at the aerodynamic effect of putting the skirt on, but we can add in the thermal effect, and it's a very small increase in cost in terms of the CFD to start to look at that, and that's the thing. You can get a lot more information out of the CFD once you know what to look for. As I say, you've got a lot of data there, and so long as you anticipate ahead of time what you're interested in studying, then you can actually see the effects of part changes on a whole range of issues. So, unless there's any other questions, I'll leave it there and come back to talk about wind tunnel testing next time when we're going to be able to go down to the tunnel. I'll talk very, very briefly here about wind tunnels, and then we're all going to get to go for a walk downstairs to actually see it. And maybe I can just answer some questions you have down there about it. So, this is better. Wind tunnel testing. It's been around for quite a long time. Ours is a little more advanced than that. But again, these are developments that were originally for aircraft, because that's what people thought. I mean, it didn't occur to them for quite a long time that aerodynamics was significant for just drag reduction on land vehicles. I say for quite a long time. 1922, they were developing parts for trains, and it's actually been quite a while since that tractor roof spoiler was demonstrated in 1953. So there's that. I mean, the 50s was when for automotive people were starting to look at aerodynamics, and a lot of the examples of what a good aerodynamic vehicle looked like were actually come up with a long time ago. It was just no one wanted to buy them, and that's certainly the problem with cars. And a lot of the challenge, which I'm sure you're all familiar with even in trucking, is just the competing priorities. If we wanted to create a really aerodynamic vehicle, we could do that. That's not difficult. The difficult part is satisfying all the other requirements at the same time. For trucking, load capacity obviously is a significant one. One of the key developments which we'll be able to see while we're down there is moving ground. Wind tunnels originally were just a fixed ground, which is clearly not as accurate a representation of what's happening outside, just blowing the wind. So we want the wind and the ground to be moving as well, which we have in our tunnel here. And just as an overview of the wind tunnel types, you can do full-scale testing in a wind tunnel. You're much less likely to be able to have a full moving ground in that situation, and it's going to need a lot of space. And when you start considering what you want to do with your testing, and testing at different crosswinds, different angles of yaw, and how far you can actually turn the truck, trucks are pretty long. It starts to become problematic. No.
Are there many places that do it, or it's just?
There are some. There are some. There's at least 4.
It's not the main type of testing.
It's. I mean, it's not. Well, I mean, some people will. It's. People have different opinions about what they can do. If you're going full scale, you've got a lot of the issues with having the full scale parts anyway, and then maybe you just want to go and do coast down testing. I mean, for us, and obviously a better compromise if you're going to go into the wind tunnel anyway, particularly with trucks, and the trucks we have, they're 8th scale trucks, which we've done a lot of work has been done outside of here as well on how small you can go and still get reasonable results, and we do get good correlation. It's important to bear in mind that different wind tunnels give different results, even though they have the exact same vehicle being tested. There is variation there, and yours is gone. But the question on the accuracy of CFD, it's the same level of accuracy as you'd get going between different tunnels. So if you're comfortable with going to a different wind tunnel and getting a slightly different number, you can go into CFD. It's the same level of error difference you're going to get. And again, if you go outside and test there you've got different air conditions. You can't control the wind's going to vary, different temperature maybe. So you're going to get slightly different answers there as well. So, I mean, people do feel like they need to do full-scale testing sometimes, but as Greg was just talking about there, if you're concerned about the EPA standards, the EPA does their verification in our tunnel here. So if whether it's accurate or not, it gives the answer that they want. So we've done a lot of work on that. And as you can see, some of these have rolling roads. Oh, that's the wrong way. Some of these don't. And just so you've got a little more background on what you'll see when we get down there, we have this thing up here. The model is just mounted to that. It's just hanging there. And the wheels are touching the ground, but the rest of the weight of the model is on the balance there, so we can measure the forces on it. And that allows us to also move the model, in this case changing the yaw to get different crosswind conditions. We wouldn't on a truck, but we can change the ride height when we're doing race cars and so on. I mean, race cars, Indy cars, we can get 50% scale models in there. The issue with trucks, as I say, is when you're wanting to test it at an angle, it suddenly takes up a lot more space in your tunnel. And then you won't be able to see this necessarily, but with the models we can put some instrumentation in there. I'd like to say a lot. We have channels for 128 pressure taps across the body, but as I say, compared to the CFD where we've got millions, it's not always that impressive. But it does give you quite a bit more information if you want to look at that, and also measuring mass flow in cooling and so on. So instead of me going through those technical details, I'd say we should just go down and have a look at it.